Hey everyone, how's everyone doing? I hope you're doing well. I'm just going to make a quick video here to go over finding the special angles or the trig functions of our special angles, but in radians. So just like with degrees, we first found a reference angle, and you did this trig function of the reference angle using the triangles. For radians, it's going to be very, very similar. We're going to find a reference angle, go back to the triangles, do the same thing we were doing with the triangles. It's just that one step before to find the reference angle when we're in radians. So one way to find the reference angle is do the exact same thing you did in degrees, but wherever you did 180 minus the theta, you're going to do pi minus theta in radians. Or if you did theta minus 180 in degrees, you're going to do theta minus pi in radians. Same thing with the quadrant 4 angles. I'm going to show you an easier way though than doing this, something that's going to make it a little bit easier. So we're going to skip these examples for just a moment. We're going to look at if there's a relationship between the denominator of your angle and the reference angle. So I'm going to develop that over to the right here, and then we'll kind of summarize in this slide over here. So this is all based on the fact, let me scroll over here, that we know that one revolution is 360 degrees, and one revolution is also 2 pi radians. If we know that, everything stems from that. We can divide both sides of the equation by 2. You get 180 degrees is pi radians. Again, something you're already familiar with. If we divide that by 2, 90 degrees is pi over 2 radians. So we're going to focus on this 180 degrees equals pi and divide that by various things. So if we divide both sides of this equation by 2, we get 90 degrees is pi over 2. If we divide both sides of this equation by 3, 180 divided by 3 is 60. Pi divided by 3 is just pi divided by 3. So we find that 60 degrees is equal to pi over 3. If we take this equation and divide both sides of this equation by 4, 180 degrees divided by 4 is 45. Pi divided by 4 is just pi over 4. So we're going to have 45 degrees is equal to pi over 4. And then finally, if we take this equation and divide both sides by 6, 180 degrees divided by 6 is 30. Pi divided by 6 is just pi over 6. So finally, we have 30 degrees is equal to pi over 6. The key here is that when you see a angle in radians that has a pi over 3, the reference angle is going to be 60 degrees. If you see an angle measured in radians that has a pi over 4, the reference angle is 45 degrees. If you see an angle in radian measure that has pi over 6, the reference angle is 30 degrees. You know, all your reference angles for the special angles are going to be 30, 45, or 60. So it's just easier to look at the denominator, pi over whatever the denominator is, and find the reference angle from that. So remember with these in radians, these are still going to be done using the unit circle with the 1s and the 0s. So those are your quadrantal angles. So you're used to already 0, 90, 180, 270, and 360. Well, those are now replaced with 0, pi over 2, pi, 3 pi over 2, and 2 pi. So the same way you did the quadrantal angles with degrees, you'll do the quadrantal angles with radians as well. So let's summarize this a little bit and look at a couple examples. I'll also go over how to do that with the unit circle that we looked at yesterday. So here's the relationship. You see a pi over 3. Remember, 180 divided by 3 is 60. So pi over 3 is going to be the same thing. So if you see a pi over 3, your reference angle is 60 degrees. Now we don't have to think about the quadrant or anything like that when you're finding the reference angle. If you see a pi over 4, your reference angle is going to be 45 degrees. And if you see a pi over 6, your reference angle is going to be 30 degrees. So if we look at these examples up top here, we want to evaluate the sine of 5 pi over 6. As soon as you see that pi over 6, that I'm ignoring the 5 for now, but when I see the pi over 6, that tells me my reference angle is 30 degrees. Again, if you want to memorize this, you can, but really the idea is pi is the same thing as 180. So when I see pi over 6, I'm thinking 180 over 6 is 30, or 18 divided by 6 is 3. You can think of it that way if you want. When I see pi over 3, I'm thinking 180 divided by 3 is 60, or 18 divided by 3 is 6, if that helps. When I see pi over 4, I'm thinking 180 divided by 4 is 45. So you're not really doing too much there other than just recognizing that pi over 6 gives you your reference angle of 30 degrees. And then it becomes just like we've always been doing. We're going to do the sine of 30 degrees. So we have our 30, 60, 90 triangle. We have the sides of 1, 2 for the hypotenuse, root 3. And if we're doing sine, we know that's going to be opposite over hypotenuse. So the sine of 30 degrees, opposite side is 1, hypotenuse is 2. Sine of 30 degrees is 1/2. The sine of 5 pi over 6 is also going to be 1/2. Now I do still have to check the quadrant. And here's the easiest way to find what quadrant it's in, because you're not super comfortable with radians yet. You can change it to degrees by multiplying by 180 over pi, but here's a way I think is easier. You know pi over 6, this piece here, is 30 degrees. Well, this is telling us we have 5 of those pi over 6s. Well, if pi over 6 is 30 degrees, 5 of those is going to give us 150 degrees. So 5 pi over 6 is 150 degrees. Again, you can get that if you do multiply by 180 over pi, but I think it's a little bit quicker thinking in terms of pi over 6 is 30. We know 150 degrees is in quadrant 2, and in quadrant 2, sine is a positive number. For the next example, we have cosecant of negative pi over 3. I see pi over 3. Right away, my reference angle is 60 degrees. Again, I'm thinking 180 divided by 3 is 60. 18 divided by 3 is 6, if it's easier that way. And if we're doing the cosecant of 60 degrees, we know cosecant is going to be hypotenuse over opposite. I still have my 30, 60, 90 triangle here. My hypotenuse is 2. Opposite the 60 is the root 3. We're going to rationalize that to get 2 root 3 over 3. So the cosecant of negative pi over 3, the number part's also going to be 2 root 3 over 3. Now in terms of the quadrant, this is a negative pi over 3, same thing as negative 60. Negative 60 degrees is in quadrant 4. And in quadrant 4, we know that cosecant is negative. And lastly, cotangent of 7 pi over 4. I see pi over 4, right away I know my reference angle is 45 degrees. So I'm going to do the cotangent of 45 degrees. 45, 45, 90 triangle, 1, 1, root 2. And I know cotangent, being the reciprocal of tangent, is adjacent over opposite. So cotangent of 45, 1 over 1, gives us 1. So the cotangent of 7 pi over 4, the number part, is going to be 1. Now I know pi over 4 is 45 degrees. I'm going to have 7 of those pi over 4s. One way to think about that without doing multiplication, we know this is 45 degrees, here's another 45, here's another 45, here's another 45, and I just want 7 of those 45 degree sections. Puts me right here at 315 degrees. You could also do 7 times 45 is 315. The key here is that this angle, 7 pi over 4, is in quadrant 4, and in quadrant 4 cotangent is negative. Okay. If you like the circle idea from today, let me just go over that real quickly with how this works for circles with the radians. So again, we know that 180 degrees is pi. If I do 180 divided by 2, that gets me to 90, which is pi over 2. If I do 180 divided by 6, 180 divided by 6 is 30, so 30 degrees is also pi over 6. And here's what's going to be nice. We're going to count by 30s. So 30 plus 30 is 60, so pi over 6 plus pi over 6 is 2 pi over 6, which reduces to pi over 3. So 60 degrees is pi over 3. If I count by another 30, 3 30s is 90. Well, 3 pi over 6 reduces to pi over 2. If I do to 120 degrees, 4 30s is 120. So 4 30s would be 4 pi over 6, which is going to reduce to 2 pi over 3. If I do 5 30s, 5 times 30 is 150. So 150, I'm going to get 5 pi over 6. And you can continue with that. 6 30s is 180. 6 pi over 6 reduces to pi. 7 times 30 is 210. Well, 210 is the same thing as 7 pi over 6. If I go to 240 degrees, 240 degrees is 8 times 30. So then 240 degrees is 8 pi over 6, which reduces to 4 pi over 3. And you keep going. If you go to 270 degrees, that's going to be 9 of the 30, so that's 9 pi over 3, which reduces to 3 pi over 2. If I go to 300 degrees, let me make this a nicer 300. If I go to 300 degrees, that's 10 30s, which means this would be 10 pi over 3, or 10 pi over 6, I'm sorry, which reduces to 5 pi over 3. And at 330 degrees, that's 11 times 30, so this would be 11 pi over 6. You can also count by 60s if you want, knowing that 60 degrees is pi over 3. So 2 60s is 120, 2 pi over 3s is 2 pi over 3. 3 60s is 180, 3 pi over 3 is pi. 4 60s is 240, 4 pi over 3. 5 60s is 300, 5 pi over 3. And for the 45 degrees, we know that 45 degrees is pi over 4. So count by 45. 45 plus 45 is 90. That's going to be 2 of the pi over 4s, which reduces. 135 degrees is 3 times 45. This is going to be 3 pi over 4. We have 4 pi over 4 at 180. 225 is 545, so it's going to be 5 pi over 4. 6 pi over 4 at 270 reduces to 3 pi over 2. And then at 315 degrees, that's going to be 7 45s. So we're going to have 7 pi over 4. And again, once you have these angle measures in radians, it's just a matter of looking at the ordered pairs and the x and the y if you're going to use the unit circle. So if I go back to that example from the worksheet real quickly, if we want to do the cotangent, that's back up here. If I want to do the sine of 5 pi over 6, from a circle's perspective, I find 5 pi over 6. Here's 5 pi over 6. I'm looking at the ordered pair. I know that sine is a y value. At 5 pi over 6, my y value is 1/2. The sine of 5 pi over 6 is 1/2. And that's it. So we get the same answer, a little bit easier